Hello everyone, welcome back to my physics YouTube channel, and I hope you're super excited to be here with me today. Now today's topic is going to be on displacement and vectors. I know that it's not the most exciting topic, but I wanted to go over it because some students tend to need some extra clarification. I also wanted to go over it because while it would be super awesome for you to pass the AP test, it would be even better if we could take all this awesome physics knowledge and actually keep it in your head and get you to fully, understand it all. So that's why we're doing this today. And in this video, we're going to just be talking about displacement and vectors, something I kind of skimmed over, and we're going to be answering questions like, what is displacement and how is it different from distance? So one important thing to note about displacement is that it includes direction, and this is what makes it different from distance because it worries about direction. So displacement isn't so much about how much ground you covered, it's more about where did you end up compared to where you started. So let's use an example. So let's say you walk 3 meters forward and then 3 meters back. Well, what would be your total distance? In this case, our total distance is 6 meters. Now that was pretty simple. We just did 3 plus 3. However, if in the same situation we're trying to find our displacement, and we had walked 3 meters forward and then 3 steps back, well, in this case we'd have a displacement of 0. Now this is because we started and ended at the same point, meaning that we have a 0 displacement. Now this shows us the distinct difference between distance and displacement, with distance being how much ground you covered and displacement, or delta x, being where you ended up with direction included. Now with all that being said, let's get into a fun topic of vectors. The name might sound familiar, but anywho, a vector is any quantity that has both magnitude, how much, and direction. So some things that are vectors would be things like displacement, velocity, and acceleration. However, things like speed would not be considered a vector because it doesn't care about direction. So when we say displacement is a vector, that means that we have to pay attention to which way something is moving. Like, is something moving forward? Is it moving backwards? Is it moving up or down? Well, depending on which directions you set as positive, that changes the sign of the answer for vectors. So say you determine up to be positive and down to be negative. Well, when you're looking at things like velocity, you have to consider the direction. If something is going in the direction that you set as negative, well, then you know that your answer should have a negative sign. Now, keep in mind that whichever direction you set as positive, you just have to stay consistent. But in the end, it's totally up to you for which directions you want to set as your positive. This is really important when we start to discuss free fall and diagrams, so this is just an important concept to keep in mind. Now, you might be wondering, how do we actually find displacement? Well, there are a few ways to calculate it, and it's really dependent on the information you have given to you. So let's go through the main ones. Now, option 1 is to use position values. In this case, position would be our x. So option 1 is delta x, or displacement, is equal to x final minus x initial. Now let's just do a quick example. So say you start at x is equal to 2 meters and you end at x is equal to 10 meters. Well, to find your displacement, all we need to do is take our final minus our initial, 10 minus 2, and that gives us 8 meters as our displacement. If you end up behind where you started, if we're thinking in terms of a number line, like x is equal to negative 3 meters and x initial is equal to 5 meters, well then in that case your displacement would be negative, and that gives you some more information about the direction. So another option you have to help you find displacement would be to use velocity and time, like say in a problem where you're given those values. And when you're using this, you just want to make sure that your velocity is constant. Okay, so for this option, we have delta x is equal to velocity times time. and that would give us displacement. When you're using this though, you just want to make sure that your velocity has the correct sign placed on it based on the direction that you defined as positive. So as always, stay consistent with your directions. That's going to be very important. Now let's use a little example using this guy with a cute little top hat. So let's say you walk 2 meters per second for 4 seconds. Well, we just do delta x, or displacement, is equal to 2 times 4, and that will give us 8 meters. Lovely. We found our displacement using this equation. Now let's do another just quick little example. So let's say this time you walk 2 meters for 4 seconds, but you're walking backwards. Now in this situation, to find your delta x, we're just going to do the same thing, but this time we're going to make our velocity negative, and then multiply that, and that will give us negative 8 meters. Because displacement is a vector, which means direction matters, we have to put that negative sign there. Alright, so the third option you have are to use kinematic equations, and if you don't know what I'm talking about, go watch my video on the big 5 kinematic equations where I explained all of these and how to use them. But these are 3 equations that will give you displacement if you need to find it. So this first one here is going to be displacement is equal to 1/2 times final velocity plus initial velocity times time. So the second one down here is going to be displacement is equal to initial velocity times time plus 1/2 times acceleration times time squared. I know it sounds like a lot. And then the third one, which is a little bit unique, is delta x is equal to final velocity squared minus initial velocity squared all over 2 times acceleration. Now, why I said this equation was unique is because when I went over the kinematic equation, this wasn't in there. And that's because this equation right here originally came from this equation. We just took this equation and isolated our displacement, or delta x, in order to rearrange and get this equation. Now this is something you're going to have to do many times throughout this course, and if you have trouble with rearranging and isolating variables, it's going to be a bit difficult. Now the next thing I want to talk about are going to be vectors and how we represent them. So vectors are going to usually be drawn as arrows, and the direction of these arrows and the length of these arrows shows just how big the vector is and what's its magnitude and stuff like that. So essentially, the longer the arrow, like that one down there, can represent something like faster velocity or a larger displacement. And when we talk about vectors, we always measure them relative to something. So say you defined right as positive, well, we measure it relative to that. So if it's pointing right, well, it's positive. We have to make sure that we're staying consistent. So the longer the arrow, it could mean a faster velocity or a bigger displacement, or overall just a bigger magnitude. Now that we talked about that, let's talk about combining these vectors with something called the tip to tail method. It's just a visual trick to kind of make the vector math easier. To use this example, say we move 3 meters east and then 4 meters north, and from the tip we're just going to move the second vector we drew to it. But just like the name said, we're going to put the tip or the arrowhead to the tail of the other vector, and that gives us this. This is our moving 3 meters east, and that was the vector representing our north. Now we draw this new line in between the tip to tails of the initial vectors we were given. This new line represents our displacement. Now to find the actual values, we could just go ahead and use the Pythagorean theorem. So we're going to plug in 3 and 4, and that will give us 9 plus 16, and then we're just going to get the square root of 25, which is 5. So our displacement for that right triangle we had is going to be 5 meters. Now I'm just gonna get into a more advanced topic, but with vectors we can actually break them into components using some trigonometry, because sometimes in a physics problem you'll get a diagonal vector like something moving northeast, and in that case you'll need to break it into its parts that go along the x and y axis. So when we break a vector into its components, we're going to have the x component and the y component. And the x component is comprised of the magnitude of the vector times cosine theta. And there, you're just going to plug in the value of your angle from the horizontal. For the y component, same thing, the magnitude, but this time we're multiplying times the sine. So far, we've been talking in the one dimension. But for 2D vectors like diagonals, we're going to need to use things like the Pythagorean theorem, and we're going to need to break vectors into their components, their x and y components. So essentially, the takeaways that we have are that vectors have direction, displacement is a vector, you're always going to want to define your directions, especially your positive directions, and that signs matter. Anyways, that's it. Please come back. I'm filming this really late at night. But anyways, these are just some fundamentals that I think it's important you get down. Now, in the next episode, hopefully you'll be there too.